Okay, so today we are going to discuss about explainability and bias in AI. So these are uh, very close to my heart, these topics. So let us start. Uh, so this tweet, this is from Geo Finton. So this appeared during the end of last February. What it asks is a very fundamental dilemma in our life. This is about whether we will trust a non-human system which does not provide you any insight, say, of how it reaches a decision, but it is uh, a very uncanny ability to provide correct decision. So this is very rightly called a black box, as nothing sort of an explanation comes out of it. So there is always a trade-off between the competency or learning performance of an AI system and its explainability. The most competent deep learning systems, they will be more difficult to explain than a decision tree or a linear classifier. But a decision tree or linear classifier may not be as competent a decision giver as deep learning based systems. So today we will try to dive into some analysis and approaches of getting and imparting explanations for AI systems. So this is a slide taken from DARPA's XI program manager Dave Gunning. So DARPA is, I think, full form is it's a research agency. So Defense Advanced Research Project Agency in the US, and they were one of the first to come up with an explainable AI program. So where it was a 4 or 5 year long program. It started in 2017 around that time, and it is still going on. And XAI is an acronym for explainable AI. And this is actually a term which is coined by David Gunning himself. Today we have some fascinating deep learning systems that's pretty accurate, especially for classification or detection tasks. I mean, you know how, I mean, we have discussed it, how deep learning systems get trained. So you feed it with lots of data, and it learns the features or the concepts by its own, which is very much task specific. So the features for a classification task or a detection, I mean, maybe different for a detection task. But they can be again shared or reused. All these things like sharing weights or pre-training, fine-tuning. That we have covered. But I mean, these then when you give these input images, test images, it will give out with what probability it is one of the objects in your known world, that is in among the categories that are in your vocabulary. So, but most of these systems are very much opaque, and people don't know why the system works. Uh, why did a network not predict, say, something else? And when can it, I mean, more I think, interestingly or importantly, when can it fail? Can I trust the system, etc. For many applications, maybe it doesn't matter much. When you are classifying a cat, or want to tag your friends in Facebook, it probably doesn't matter much. But imagine this happening for a medical diagnosis. I mean, these questions arising: where can I trust you? When can it fail? Basically, so imagine these are happening for medical diagnosis application, or say a military application. So answering this type of why questions actually have many practical significances. A model incapable of providing explanations for its decisions will have serious trust issues. So explainability, in addition, will help the data scientists uncover the dataset biases also. So we will see how that can help. I mean, explainability can help to discover dataset biases, and ultimately, with discovered biases and mitigating it, can create better models. So this is the goal of the XI program, to come up with a system which may use different algorithms, or may use a human computer interaction method to understand why it's happening, understand why not even, when it is failing, when it is succeeding, and when to trust, etc. So there is, I mean, this is also another slide taken from that DARPA XI presentation. So there is always a trade-off between the competency or learning performance of an AI system and its explainability, as I told in the very second slide. I think the most competent deep learning systems will be more difficult to explain than a decision tree or linear classifier, and that's what is meant by these orange dots in this curve. And you can think of it, I mean, and a kind of typical analogy would be, these are much like teachers who are completely brilliant but unable to explain anything to a student. Or you can have great teachers, even though they are not, say most recognized researchers. So the goal of this DARPA XI program is to move this curve to, so yeah, this one, to the right, so that both better explainability and performance is achieved. So this to this. Not only that, the explanation, I mean, the expectation is that the increased explainability of the models will act like a positive feedback, uh, which will help to create better models, as people will have far better insight about the workings of the model. So that is kind of the goal of this program, XI program. So this is the basically the competency, and this is the, I mean, in the performance you can say, and this is the explainability axis. Now let us go through a little bit of why do we need actually explainable AI. So we have said about that, okay, it will help to get us far more insight, or it can even help us in discovering bias, which will in turn help in getting better models. So let us see with some more examples, some concrete examples, why do we need explainable AI. So this is an image from FMOW dataset. FMOW is a functional map of the world. So it has this overhead imagery of different facilities, different types of facilities in or satellite images. This data, so I mean, facilities means here buildings, shops, hospitals, these kind of facilities I'm saying. And the task of this data set that was given, it came as a part of a challenge, is to classify the images. So a state of the art classifier trained in this data set, I think it was, the values that I'm showing is ResNet 50. So detecting that it's a solar farm with 63% probability, or but at the same time the classifier also thinks that it is a shopping mall with 23% confidence. So this seems like reasonable answers. You might want to know, why does the classifier think that this is a solar farm or a shopping mall? What about this picture that led the classifier think that it's a shopping mall? uh, that's why you need explainable AI, some way to rationalize decisions made by the classifiers. So when we apply some model, the so-called explanation generation model or explanation model on the classifier made decisions, it tells us that when the ResNet classifier thinks it's a solar farm with the 63% probability, it is focusing on this part of the image. This is the highlighted part in red. So the red means here that it is more important for this network, for this model which we want to explain its decision of. This red part is more important when that model, the model that we are trying to explain, gives one decision. It says things that it is a solar farm. The blue means less important. So for example, we see that the network thinks that this image, that the image is that of a solar panel. It is, when it is thinking that, then it is looking at the roof of this facility, whatever that facility is. Maybe perhaps there are some solar panels here. These black parallel lines, maybe they are solar panel, or it is looking for this, or if there is a good chance that the roof like area will have solar panels. I mean, if a facility has a solar panel, then it is most likely that it will be using its roof space to have the solar panel. But when we ask it to explain, ask it means here the explanation model. So when I say model, there can be two things, but I'll try to disambiguate between these two. So one is the model that we want to explain, that is the ResNet classifier, or maybe some detector, or maybe some captioning model. And another is that explanation model, so which generates the explanation. There are some approaches which will not go into detail, which inherently comes with explanation. For example, one of them is decision tree. We can get a path. So there are other neural network architectures also, which are called modular neural network, that we will not go into. But in our discussions, if we say model, sometimes it means the model that we want to explain, and sometimes it can mean the model which generates the explanations for those model. But I'll try to disambiguate as far as possible. So, but it should be clear from the context also. So when we ask to explain the decision shopping mall here, it highlights other areas. I mean, it's not these roofs, it's these parking lots or these highways or freeways beside the facility. So it becomes clear that the classifier might have learned when it is trained on getting trained on this FMOW dataset, that shopping malls are often near the freeways, or maybe shopping mall comes with parking lots. So this is when it is classifying it as shopping mall, it is probably looking for these parking lots or the freeways. So these explanations are actually generated by one of the recent models of us called RISE, or randomized input sampling for explanation. That's an acronym. We will discuss how it works in detail, not today, but in the next lecture. So this is another example. This is an image from the Pascal dataset, and you know Pascal dataset has 20 object classes. The classifier predicts that it contains car with 64% probability, which is quite high if you think that it has only 20 object classes. That means the chance probability is basically 5%. So why do you think it might be predicting a car? There are cars present, of course, but let's see what the explanation model says. So this is again a ResNet model giving this probability, and this is the explanation model giving the explanation behind the decision card. So it says that when the network decided that the image contains car, it actually is not looking at the cars that are parked here. Instead, it's mostly looks at this monitor and maybe using the road somehow as a context. So sometimes we might want to know why a model is predicting something, so that we can improve them by asking, not grounding its decisions on wrong concepts. This is a wrong concept as a car, right? Or even so that it doesn't ground its decision more on the context, but on the actual object. Basically, we want the AI models to be right for the right reason and not right for the wrong reason. So this is an example of right but for the wrong reason. Okay, so we want that it should be right for the right reason. This is another example where the classifier predicted a cow here with 76% probability, and this is again from the Pascal dataset. But we see that all of these are sheep. So this is a wrong classification even, or wrong decision. So why do you think that it can be? I mean, the ResNet 50 model is thinking that it is a cow. So this is the explanations generated again by the RISE model, or the explanation model. Now, if we look at these explanations, we see that the decision is based mostly on this one sheep, that is, or kind of this one black sheep that is present here. It actually made us dig deep to the cause, and it turns out that this particular dataset Pascal has a lot of white sheep and lot of black cows as well, just like real life. I mean, black sheep are very rarity, right, in our life. So it is true. I mean, it is truly reflected in the dataset also. So the classifier trained on this dataset has learned to correlate an animal-like shape with, say, black color to a cow, and anything which resembles like an animal with white color, possibly to a sheep. So that's the bias present in the dataset. So the dataset is biased towards sheep with white color and cows with black color. So this dataset, this bias present in the dataset has influenced the classifier, and we can discover the effect of such inherent bias. Why is it inherent? Because it is coming from the real life with the help of such explanation. This is another example from a recent paper in ECCV 2018 from UC Berkeley and Boston University. So this is an image. This is for an image captioning model. So here is a comparison that is shown between two different image captioning models. So now you have a fair bit of an idea how image captioning models work and so on. So I'm not going into the detail of that. So the left one shows the caption generated by a traditional model, where you have these images, you encode or get the encoded features, then you pass it through a recurrent network, and it generates this: a man sitting at a desk with a laptop computer. So we see that it is actually generating an incorrect gender word. The explanation model, so when we run an explanation model on this for the word man, so it is the explanation that is generated for this particular word man in this caption. So we see that it is actually the model, the captioning model is actually looking at this computer or this monitor present in this scene. And this is because of the bias in the caption dataset. So due to our social prejudice, you can say, computers are still not aplenty with women, and thus most images we have of a person with computer, the person is generally a male person. Thus the captioning model also picks up this correlation, this uncanny correlation, to generate such biased gender words in presence of computers. Now the right hand side actually shows the captioning model from this paper, this paper, Women Also Snowboard, Overcoming Bias in Captioning Models. We will actually discuss about this paper during the last half of this topic, which may be tomorrow or even maybe day after tomorrow. This paper is again very close to my heart. So it is showing that using this model, we are generating this caption. Model means the captioning model, a woman sitting in front of a laptop. And not only that, when the word woman is generated, the explanation model actually focuses on the woman, not on the computer. So it actually kind of grounds his decision on the actual object. So right for the right reason, and right for the right reason, and here actually it is wrong for wrong reasons. So this is like the need for explainability and transparency in 3 stages of evaluation, and this is one this slide is motivated from this famous grad camp paper. So it's a very good paper to read in, and we will discuss it tomorrow, not today. So the first stage is when AI is significantly weaker than humans and not yet readily deployable. For example, open-ended visual question answering or automated medical diagnosis, etc., which are not still at par with, say, human level performance. I mean, it is good when you have lots of training data, supervised or annotated training data, and then the training distribution and the test distribution, they are pretty much same. Then it's probably doing good, but it's not yet readily deployable in on the wild, so to say. So the goal in such use of AI is the goal is to transparency and explanation is to identify the failure modes, because it is not at par with the humans yet. When AI is at par with humans and readily deployable, so example is of course image classification on a set of categories trained on sufficient data. So there is this catch that it has to be trained on sufficient data, but still it is doing pretty good consistently. So here the goal is to basically establish, the goal of explanation or getting transparency is to establish trust with users, that okay, I can trust the classification system, it will do basically good when it is asked to. Then the third stage is when AI is actually significantly stronger than humans. So this is when it is weaker than humans, when it is at par with humans, and it is significantly stronger than humans. And actually, we have seen that these chess or Go playing bots, these AI agents, they have defeated the human players. So and not only human players, they are some of the best in the world. For example, these Go players. So here the goal of transparency or explanation is machine teaching. So a machine teaching a human how to make accurate predictions. We can try to get feedback from the agent and to improve ourselves. So these are basically the three stages of AI evaluation, and I have till now covered why we need explanations, why they are basically useful. Later I will go into different forms of explanations and so on. So before that, I'll again stop for questions if you have, and I will actually see the chats if there is any question. That if you have anything, please unmute and ask. Otherwise, I'll go ahead and continue. Okay, so this is now different schools of thought. So we have different schools of thoughts for explainable AI. So there are different methods that we can categorize into the explainable AI works. Some of these are occlusion based methods, some are activation or gradient based methods, there are deconvolution based methods, and theory of deep learning. So in a very nutshell, occlusion based methods try to suppress some part of the input. In our case, it may be images, or sometimes they have been employed in 1D signals, audios, and so on. And we'll see what effect that part which is occluded has and the decision. So it will give the importance of that part towards the decision. So those are mostly occlusion based methods. Then activation or gradient based methods, this is again similar. So gradients can give the importance of basically the input, part of the input which is affecting the decisions. We will have a detailed discussion of activation or gradient based methods today itself. And then there are deconvolution based methods. It's called deconvolution. It's a hacky way of basically backpropagation. We will not go into details of that. And theory of deep learning basically comes up with tools of basically mathematical tools with different bounds and so on. So we actually will go into these two things. We'll go into details of occlusion based methods and activation or gradient based methods. So before we go into that much detail, actually let us discuss a little about this subtle difference between introspection and justification, or sometimes the justification is called post hoc rationalization. So explanation can be of different form. So I think whether it's an introspection or a justification plays an important role. So introspection gives more of why a decision is made, or kind of how a decision is made. Sorry, why is justification. For example, let's say we have an image classifier which says that an image is an element. Say you have an input image and it says that it has an element. And we also see that each time an elephant image is presented to the model, some filter, say second filter in first layer, or say 84th filter in the last one layer is highly activated. So if we give this as an explanation behind the decision, that okay, this filter and that filter and a combination of these filters have this high activation. So for each elephant, and now all these filters are having high activation for an image. So this is a elephant. So this doesn't make, I mean, this is perfectly fine as an explanation. I mean, how the inner working goes on, the inner wiring between the different layers, different neurons in the network goes on. But it's an introspection, right? I mean, how the model determines its final output, but may not make much connection to the user. That's the kind of a disadvantage of introspection. So we may be technically correct that it's an explanation, but the use of the explanation to basically impart trust, you getting more transparency, that may not be very readily satisfied. Instead, if some form of explanation comes in this way, that it's an elephant because it has a trunk and say two long teeth, that is, the model is looking at these two parts when making the decision, then it is a justification. It may not be, it is that it is explaining exactly how it is, how the decision is made. It is actually looking at the trunk or long teeth. It may be that, okay, this is coming from some non-discernible features getting activated and so on. But if we give, if we can give such an explanation, then actually it basically explains that it is, or it makes connection to the user, and it imparts the trust. I mean, so it's a justification. Of course, it's a post hoc rationalization. It is exactly not how, it may not exactly be how it is made. So justification many times make the user feel good than an introspection, and introspection may not make sufficient contact with the given user, and in many cases it's they are non-expert. So we want to explain decisions to a non-expert. Just try to think about a medical diagnosis problem, so where an explanation can actually, a medical practitioner, a doctor or physician may understand well that, okay, whether this is a good decision or bad decision. But when you have to make a patient understand that, then you have to be in the level of the patient, right? So that explanation may have to be that in that level. So which is better served, I think, by justification, not introspection. So what makes an explanation good? This simplicity, clarity, completeness, consistency with prior beliefs. What is consistency with prior beliefs? It may be that it suddenly should not tell that the model thinks. Suppose you are actually explaining a cat classifier, and if you tell that, okay, the model thinks it's a cat because it has a trunk, it actually is not consistent with the prior beliefs, because a cat doesn't have a trunk, right? So there is a very good anecdote of one of the best explainable AI researchers, Richard Karauna, from Microsoft Research. So when he was a PhD student, probably in 90s, so they actually made a medical diagnosis tool using that time. Yeah, it was using a neural network at that time, and it was actually predicting the readmissibility of patients with pneumonia. So what is, I mean, kind of, what is the chance, means it will tell whether to readmit or not a patient who is suffering from pneumonia. So they found surprisingly that patients with asthma and having pneumonia are likely to be admitted less given by this algorithm. So this was surprising. So they actually, I mean, this is not consistent with the prior beliefs that if you have pneumonia and if you have prior history of having asthma, you actually need to be hospitalized with more care. The thing is surprising because the ML model or the neural network model gave that it should not be. The reason dig up the reason, and they found that actually the data set had persons who were actually admitted to the hospitals, and they received better initial care because they knew that this person has asthma. So they received better initial care, and that's why their chances of basically fatality gone down, and that's why the dataset says that people with asthma but having pneumonia will die less. So that's kind of inconsistent with the prior belief that okay, people who has pneumonia and asthma should not actually, the prior belief is that you should actually admit it to the hospital, which is true. But if an algorithm gives something which is inconsistent, then it's wrong. So this is one small slide with introspection and justification. There are lots of literatures that are coming out with these debates. So I'll just encourage you to go through it, and if you need some more references, I can readily give it to you. Okay, now these different forms of explanations. So these are visualizations. So visualizations are basically the saliency maps or importance map that we have seen. that what parts are basically more important as explanations and what are not for behind a decision. So that's those are visualizations. Textual justifications can also be generated, that okay, there are some works which generates textual justifications. Okay, this is a particular type of a bird because it has red beak and this kind of wings and so on. So it can basically give textual justifications also, generate the explanations. There can be graphs, networks, algorithm, computers, processes, proofs, etc., which are mostly coming under this theory of deep learning part of the explainable AI. And there can be actually cause effect relationships which are gaining momentum in explainable AI, literature, which are causal models. So it tries to find the actual cause, and most of the times it has been seen that correlation is the main cause, not cause, correlation is the main reason which due to which sometimes the models fail. So let us go into this activation or gradient based methods first. So we have seen that telling just that one neuron or a bunch of neurons is greatly activated as an explanation, as a form of an explanation for a decision, does not convince people. So the natural question comes, can we instead provide the users with regions in the input, say for an image classification system, image regions, which is highly influential behind the decision. That's what we have seen, right, for these rise given explanations. So what can be a way to get how influence an image is or image region is? It can be a derivative of class score with respect to input region. So a class score or probability, it gives you that okay, this is the probability that this image contains a cat or whatever, this image is of a cat or dog. Now how sensitive this score is with respect to the input region can be obtained if we can compute the differentiation or the derivative of the score with respect to the input regions, right? And one of the big advantages, we already have tools for it, which is backpropagation. So before we go into backpropagation, this is just a recap of the forward pass and backward pass in neural networks. So these slides we have already seen, right? But maybe long ago. So it's good to have some. So these are different layers, and this is say input, this H0 or X, which are same. These are hidden, sorry, excuse me. So hidden layer pre-activation, these A's, and these goes through the activation function and gives the hidden layer activations, which is getting this multiplied with this weight matrix and biases to get again the next pre-activation and so on. And then Y is the predicted output, which you can think of as a function of X and theta. Theta is the collection of all learnable parameters, that is W and B. And these things you know, right? The WH plus B and so on. So I'm not going into much detail, but just it is that I'm brushing things up so that things come to your mind. Now, this is backpropagation again in a nutshell. So for gradient descent, we need to compute this. In gradient descent, what we do is we want to find the gradient of the cost function, which is denoted by this J, which is some sort of a difference between the predicted output and the ground truth output. So this loss function J with respect to the parameters, which is weights in the Lth layer, that is the ijth weight in Lth layer and the ith bias in Lth layer, and this Ij can for all Ij and L. That is the goal of general backpropagation, or when we are learning, when we are training. And you know, backpropagation consists of intelligent use of chain rule of differentiation for computation of these gradients. Now we have told that we want to compute the gradient of the score function with respect to input, right? That gives us how the score function or the probability changes when we change small part of the input, right? So it is with respect to input. So if we change small part of the input, how does the activation at the last layer, that is the probability score, the softmax score, or even just the penultimate thing, that is the score or logics which are softmax to get the probability. How does that change with respect to a slight change in the input? So if that score changes a lot by a slight change of some input, some part of the input, then that part of the input is very much responsible for or it is more important towards making that score high. So that is basically the idea why we want to go or want to have this gradient of activation of any neuron, it is saying, but it is basically the gradient of activation of the last layer neuron with respect to input, with respect to the input. But if we say make it more generalized, if we want to have the activation of any neuron in any layer with respect to the input, this is important. It is not with respect to the weights or the bias, with respect to the input, that is this X in the last slide here. What will we do? Can we use backpropagation? If yes, then how? That is what changes need to be incorporated. So first of all, let's say we want to have the the derivative of the activation at activation J, or the neuron J at layer K. So we want to compute this del Hjk of del Xi with some input. So the jth neuron in kth layer with respect to the ith input. So first thing we will do is we will not do the full forward pass. So stop after the kth layer. So here we are discussing about a general neuron, not the last layer. So we'll extend it to the last layer later. So again, just to be clear, we are trying to compute this thing, which is the derivative of the activation of jth neuron in kth layer with respect to the ith input. So first thing we need to do is we don't need to do the forward pass after the kth layer. Then this is back propagation in a nutshell. I mean, this is back propagation when we are trying to basically do this with respect to the weights and biases. This we have seen earlier. So these are, I am giving the same slide, I'm copying the same slide, so the equation numbers are also same. So first we want to have the we not want to have, we have the derivative of the loss with respect to the ith neuron in lth layer, activation of ith neuron in lth layer. This is the derivative of the activation functions. We get these, then we use these to get PIW and so on, right? We have seen that. This is not yet what we are trying to do. That is this. This is just traditional backpropagation where we want to find the derivative of the loss function with respect to weights and biases, right? Now, the very first thing is to compute when we do basically the change, or we will want to see what are the changes that needs to be done in this traditional backpropagation when we want to compute the del Hjk with respect to del Xi. So first thing is to compute this. So this J has to be replaced with del Hjk, or kind of J has to be, J means this capital J, that is the loss, that has to be replaced with this H small jk. So this will be then del Hjk and del K, Ik for this will be for, this is in general for all L, but first we need to compute it for the last layer. Last means here the layer we are interested in. So this will be one.
Okay, so due to some glitch, I think the audio was not audible. So let me go back a little and let me start from somewhere where we, I think you guys were not, from somewhere you guys were not able to hear. So we see that the very first thing to compute is this, that is we don't do this forward pass beyond this kth layer. And in traditional backpropagation, we have seen that we compute this loss function the derivative of this loss function with the ith neuron in the lth layer for all i's, and then we get the derivative. From that, we get the derivative of the loss function with respect to the ith neuron in the lth layer, which goes here to get the derivative of the loss function with respect to the bias, and so on. So the first thing is that we are not considering this loss function. We are considering the kth layer's jth neuron. So first thing is to replace this j. So now if you replace this j with this hjk, what you will be doing, the first thing is in this kth layer, you will find the derivative of this thing, which is del hjk of del I k for all I in the kth layer. It will be all 0. So derivatives of hjk with respect to all neurons in kth layer are 0 except for the jth neuron. So we'll have only one there as the derivative. So this thing actually, del hjk, del il, all will be basically 0 except for the jth neuron in that layer. So you now we colloquially say that then what you do is you set this derivative value. So this is a gradient vector for the kth layer. If kth layer has say n neurons, then this will be a n length vector. All of them will be 0, just one will be there, only corresponding to the position j. Then you basically go ahead and do this back propagation with respect to AIL. L means first L is equal to K, then L will be K minus 1, K minus 2, until we reach the input, that is, this one, H0, or the 0th layer. And that way we will get ultimately this value, right? When L minus 1 basically is 0. So this slide, from this slide to this slide, actually these things are changed. Notice the change from J to HJK. So it is actually very easy. If you go back to your back propagation slide, the only thing that we are changing is the J to HJK, and the corresponding changes that needs to be made. All the other formulas and everything are remaining same. So we can basically use the tool in our hand, that is back propagation, to get the derivative of any activation in any neuron with respect to input. You can use the same formulas for getting the derivative of any activation in any neuron with respect to the parameters also. But for the explainability purposes, we want to get the activation of the last, one neuron in the last layer with respect to the input neurons. So that is, or the inputs regions. So that is kind of the connection. I hope it is clear. The connection is clear. I will actually stop a little. I might have just 2-3 more slides for today, but I'll stop a little and wait for if there is any questions and if I need to be a little more clear on that. I'll probably wait for 10 more seconds. Okay, let's actually then go ahead. So how does it help? So helps to understand what excites a neuron the most. This is the interpretation of the gradient of a neuron activation value with respect to the input, right? So because the numerator is the activation value of the neuron and the denominator is the input value. So with respect to the input, how does the excitation value of the neuron gets changed? So high gradient of an output neuron activation value, that is the classification score in the last, if it is the last neuron, with respect to a certain input pixel, implies a small change or perturbation of that input pixel has a large effect on the classification score represented by that output neuron. So that pixel is important towards making the classification. So that can be an explanation, right? So this is like this is the very first kind of, I regard this is the very first work on explainability. It was way back in 2014, again from the same group in BGG Visual Geometry group, who came up with the BGG architecture, Simonian, Zimmerman. They were also involved in that paper, in BGG paper. So deep insight convolution networks. You can read that paper. It's very simple to read now that we have came to know about these tools. So these are some results when you actually are computing the derivative of cat, this is a dog, so dog score with respect to each of these input pixels. We see these are high values, so it is expected that it will be high on the object that is there in, I mean, or that it is predicting. So these are some cherry picked examples, but we'll see that later many works are actually basically leveraging on this idea. So this is like for a particular type of a monkey, this is the activation values, I mean kind of the gradient values. These are the gradient values. So gradient of dog score with respect to these inputs, gradient of say monkeys with respect to these inputs. Sorry, these things are visualized here. So again, helps to understand what sort of images generate maximum score for this particular class. So now this can be used to basically do a different type of optimization problem. So in training the neural networks, the goal of the optimization problem was to basically generate, or how can I say, change the weight values, the learnable parameter values, the weights of the network with respect to after getting the derivative of the loss function with respect to the weights. So but here we can use a backpropagation to get an image, not a network, that is weights of network for a particular class, which actually generates the maximum score. So it is not that to get weights of a network which generates minimum loss or maximum negative loss. No, it is get an image which maximizes the score for a particular class. So this is the problem particularly. So this is for a class C, for a particular image, ACI is the score for class C, or you can think of it as the probability of class C given that image, and this is a regularization term. So this regularization term restricts the image to have small number of pixels having very high intensity. So we'll see different variations of this in later slides. So this is the last slide I'll be discussing today. But this is the optimization problem. See, the optimization is done with respect to I, that is the image. So this is looking for an image I where SC is the score of class C, and we want to maximize this SC. So if we do this, it falls into these discussions that we have, right? So we want to get this del SC del I for, I mean, del capital I of small I. Small I is the ith pixel in capital I. So we can actually get it using the tools that we described in earlier slides, right? So if we do that, we see that this is the image which gets the maximal activation score for a dumbbell class. So we can see that a lot of dumbbells are there. It tries to put kind of a copy of different dumbbells in different places, cups, views. And this is, again, this slide is taken from Anand Garpathi's course in CS60010 in winter 2016 version. And he has this famous quote, maybe one goose is good, but 10 goose is much more likely good. So this is what it is trying to attain. So it's trying to put goose in everywhere in this image to get a really high activation score for goose in the last layer. So I'll stop here today, and we will actually continue with some extension of these optimization based approaches to get more kind of far better looking images, more realistic looking images. So we will see that tomorrow. Okay, let me actually stop here and wait for some questions if you have. Maybe just let me wait for 10 seconds more. If you have any questions, you can just ask. Okay, thank you then.